Suppose I were to ask you, what's so special about these two factoring problems? Well, if you just take a blind guess or want to say a famous mathematician or looked at the title of the video, you might answer Pythagoras. And then, of course, I'd ask you, why did you say Pythagoras? And you'd say, because the answer is always Pythagoras. Well, if those were your answers, then congratulations. You've just intuited one of the foundational results in algebraic geometry. So we're going to talk about factoring and Pythagorean triples as a teaser intro to algebraic geometry. Most of this video, really all you need to know is college algebra. At the very, very end, we will talk about some connections to group theory and elliptic curves and things, but for 90% of this video, as long as you have solid algebra skills, you should be fine. All right, so the origin of the question we're going to look at is from when I teach factoring. I always give this sequence of examples. So x squared plus 10x plus 24. As you know, you need to find two numbers to add to 10 multiply to 24, which are 4 and 6. So and then I say, well, what if I change the middle, make it x squared minus 10x plus 24? Well, now -4 and -6 do it, and so that's great. And then I say, well, what if this time I change, instead of the 10, change the 24? And most students at this point are going to try to use -4 and 6 or 4 and -6 or something, and those add up to 2 or -2. So they'll say this one doesn't work. I mean, they'll throw their hands up in the air and say, doesn't matter what combination of pluses and minuses you try, you're not going to get to add up to 10. Of course, the right thing to do is to forget about 4 and 6, and then you can see that there are other numbers, namely 12 and -2, that work. So I like giving this example because oftentimes in math, you start a problem, you can see something that's very close to the right answer, and you can kind of tweak it and get to the right answer from your initial guess. But it's just as often that you see something that looks very close to the right answer, and you try tweaking it and you just can't get it to work out. And the only thing to do is to throw it out and start again. And so I like teaching that lesson early on. So this is one of my go-tos for that reason. Anyway, I got to wondering, how common are factoring problems like this? So how often do you have integers m and n where x squared plus mx plus n and x squared plus mx minus n both factor? And the answer winds up being very, very cute. So these both factor if and only if there's a Pythagorean triangle with hypotenuse m and area n. So one little disclaimer, I said natural numbers here, but we're really going to do integers for the rest of this, just to not worry about signs. So like 3, 4, -5 would be a Pythagorean triple for purposes of this video. Okay, so for example, the one I always give is 6, 8, 10. Sure enough, hypotenuse 10, area is 24, and those both factor. You can take your favorite Pythagorean triangle. So mine's always been 20, 21, 29. Sure enough, it gives you two guys. They both factor. If you want to be a mean teacher, you can make a whole quiz out of problems just like this. All right, so how do you go about showing something like that? We're going to have two proofs. The first one's very basic algebra. It's really simple, but it's really not intuitive at all. And even though it shows that we do have this Pythagorean connection, it doesn't explain where it comes from. So after that, we're going to give a second proof that's systematic using geometry. It's going to involve a lot more drudge work than the first one did. And to be honest, it's even worse at explaining the Pythagorean. I mean, it's not only does it not tell you why there's a Pythagorean connection, it also doesn't tell you that there's a Pythagorean connection unless you have some other kind of formulas in your back pocket that you may or may not have already learned. And so That's not very satisfying. But then after that second proof, we're going to go back and think about it more abstractly and realize that just the systematic nature of it implies that there was going to be this Pythagorean connection, not only to this problem, but to a whole class of problems just like it. Okay, so first let's do a little prep work. Our assumption is that those two guys both factor. Of course, we know the quadratic formula. If we want those to factor, we just need the roots to be rational. To figure out whether they're rational, just look at the square root part. So if I have rational roots, I need this thing under the square root to be a perfect square. So doing that for both of our guys, the first one, b squared minus 4ac, is m squared minus 4n. I need that to be a square. And the second one, I'll have m squared plus 4n needs to be a square. And if we just add and subtract these equations to write it a little differently, I've got p squared plus q squared is 2m squared, and p squared minus q squared is 8n. And so your first little homework exercise, if you want to do it, is to check the second equation is actually redundant. So if you have any solution to this first equation, p squared minus q squared will always be divisible by 8. And so you'll be able to solve the second equation as well. If you don't want to do that, we'll actually see it as we keep going. All right, so we want to find all integer solutions of p squared plus q squared is 2m squared. And of course, on the surface, this looks very similar to Pythagorean equation, a squared plus b squared is c squared. But since we're looking for integer solutions, I mean, we've got squares everywhere. Square root of 2 is an irrational number. So it's not obvious offhand why the integer solutions of these two equations would be related to each other. But as oftentimes happens in math, we just stumble across a random formula from algebra class that magically connects them. So the name of it's the parallelogram law, but you can just check it by distributing and combining like terms. So a plus b squared and a minus b squared, if you combine all those like terms, you'll get 2a squared plus b squared. And that connects these two equations, because if you give me a solution to the Pythagorean equation, all I have to do is set p equal to a plus b and q equal to a minus b and m equal to c. Then this parallelogram law here says exactly p squared plus q squared equals 2, and then m squared. So if you give me any Pythagorean triple, it gives me a solution to my factoring equation. And I can just as well reverse this. So if you give me any solution to the factoring equation, I can solve backwards for a, b, and c. Notice that if p and q solve this factoring equation, they have to have the same parity. So these will still be integers. So if you give me any solution to the factoring one, I can back sub and get a solution to the Pythagorean one. So I've got this one-to-one correspondence between the integer solutions to the Pythagorean equation and the factoring equation. And we see in this correspondence already that the m has to be the hypotenuse of the Pythagorean triple. So the only thing left is to figure out what does n have to be. I'll go back. N was p squared minus q squared over 8. We can factor that guy. And we recognize these factors, p plus q over 2. That's exactly our a, same thing. P minus q over 2 is our b. And so we get 1/2 AB, which is the area. So that's it. That's the end of the first proof. The only time trinomials factor that way is when m is the hypotenuse, n is the area of a Pythagorean triple. Well, it's very nice. It's really simple, but it would have been pretty hard to come up with if you didn't think of or didn't remember that formula. And so it leaves us with some questions. I mean, is there a systematic way to have gone about a problem like this? Was it just a coincidence that we had this formula that connected the two together? I mean, in other problems, should we expect to find a formula like that? If so, how do we figure out what it is? And then we got this solution in terms of Pythagorean triples, but is there a systematic way to find all the Pythagorean triples? Many of you may know the answer to that, but if not, we'll look at that too. So let's try going about it a different way. So again, really what we need to do is find the integer solutions of p squared plus q squared is 2m squared. The name of this process, if you want to learn more, is called finding the rational points on a projective conic. So hopefully those words the context will make a little more sense as we go along. But anyway, so the first step is just find one non-trivial solution. So in this case, just putting p, q, and m all equal to 1, we get a solution to the equation. So that's not bad. In general, this is actually the hard step, though. It's possible that there aren't any solutions to the equation. So, for example, if you did p squared plus q squared is 3m squared, then you can do some mod 4 check and see that there actually aren't any non-trivial solutions to that equation. And likewise, I mean, in general, figuring out whether there are solutions is tricky. And even if there are solutions, actually finding one can be quite tricky as well. So if you want to learn more of this story, you can look up words like the Hasse principle and Pell's equation, things like that. But we're going to stick to the case where we can just look and see what one solution is. So somehow we found one solution to this equation. How do we find the rest of them? Well, the first thing we do is we switch to affine coordinates, which is all that means is we're going to divide everything by one of the variables. So we did have p squared plus q squared is 2m squared. If we divide everything by m squared, then we just get, well, if x is p over m, then x squared and y squared, and then 2. So we've just kind of gotten rid of one of the variables by dividing by it. And what that does is that switches our problem from being an integer solution problem to now we want the rational solutions. And again, our 1 point in integers gives us a rational point. So now that we've kind of switched to this rational equivalent, we're going to graph it. So here's 1, 1 that we know. We're looking for this other rational point. The first thing we realize is if x and y is a rational point, then if I draw this line connecting it to 1, 1, then the slope here has to be rational because it's just y minus 1 over x minus 1. And we're going to see the other way around. If this slope is rational, we start at 1, 1. Wherever it intersects this circle, it's going to wind up giving us a point with rational coordinates. So we wind up being able to parameterize all the rational points just in terms of the slope. So, okay, so let's do that real quick. Well, what equations does our point have to satisfy? Well, it has to be on the circle, so x squared plus y squared is 2. And it has to be on the line, so y minus 1 is our x minus 1. And so we can solve the second one for y, plug it back into the first one. Just skipping a little algebra here. We get a quadratic equation for the x coordinate. And that may look a little scary because we got this kind of arbitrary r in there. It's quadratic. We could use a quadratic formula or something to solve it. But we can actually solve this really easily. If we think about where did this equation come from? It came from saying the point xy solves these two equations. Well, do we know another point that solves these two equations? Yes, we do. It's the point 1, 1 that we started with, right? I mean, 1 plus 1 is 2. 1 minus 1, so 0 is 0 for the second one. So this quadratic equation we got said that the x-coordinate of a point satisfying these two should be roots of this guy. Well, one solution is the x we're looking for. The other one is the x of this point 1, 1. I mean, since 1, 1 satisfies those two equations, the x-coordinate 1 should satisfy this quadratic we got. And sure enough, if you plug x equals 1, you can see pretty easily that all the r squareds and r's and stuff will cancel out. So one of the solutions is 1. And then we can get the other solution real easily if we just remember from our algebra class that the product of the solutions is this last coefficient divided by the first coefficient. Okay. So the x we're looking for, well, is 1 times x, but 1 times x is the product of the roots. The product of the roots is this last guy divided by the first guy. Okay. So that's the x-coordinate of the point we're looking for. In particular, we see, just as we kind of suggested earlier, I mean, we know if x and y are rational, then r has to be rational. We see now that if r is rational, this x-coordinate is going to be rational also. So we really do get a rational point where this intersects. And so you can repeat this process, find y as well. It's given by something really similar, just a couple signs different. So we wind up getting a 1-to-1 correspondence between the rational numbers and the rational points on this circle. So rational number, so these are going to be slopes. So infinity is for the vertical line. So each slope corresponds to a rational point on the circle. So r corresponds to where that line intersects, except for not the 1, 1, but the other intersection. And then any point except for 1, 1 corresponds to, well, draw the line from it to 1, 1 and find the slope. By the way, 1, 1 itself would correspond to the slope of the tangent at 1, 1. But anyway, this is the basic idea. Okay, so that's great. We found all the rational points on the circle. How do we translate that into what trinomials factor the way we wanted them to? Well, usually the next step you do is you'd write this rational slope as being a fraction. So if I write this as u over v and plug that in, get rid of the denominators. So I get x is this guy, and same thing for y, just a couple sign changes. We remember our x is p over m, and y was q over m. So if we took this u over v in lowest terms, then this guy will be in lowest terms. So the m has to be some multiple of the denominator. So m is some multiple of denominator. P is some multiple, well, the same multiple of the numerator. And likewise, q is the same multiple of the other numerator. So if we just cared about that factoring equation, the p squared plus q squared is 2m squared. Well, all the solutions look like this, where k, u, and v run through integers. If we want to go back to the trinomial thing, figure out what n is. So just like before, and we've got our p, q, and m. N is p squared minus q squared over 8. So if you add them, the u squared and v squared cancel. If you subtract them, the two uv's cancel. So anyway, there's your n. So that's great. I mean, if what you wanted to know was what values of m and n will give you those trinomials where they factor both with the mx plus n and the mx minus n, well, the answer is take these two formulas for m and n, let k, u, and v run through the integers. That gives you all the trinomials. But now we're wondering, well, where is Pythagoras involved in this? And on the surface, it's not obvious at all that this should have anything to do with Pythagorean triangles, unless you happen to priorly know the parameterization for all the Pythagorean triples. So Euclid solved that problem. He said that A was, well, this thing here, which we recognize as being this last term in our n. B, 2kuv, we see that, well, up to the minus sign is there in the middle. And C is the same as our formula for m. So if you happen to already have these formulas in your back pocket, you can see, oh, M has to be the hypotenuse, N is 1/2 A times B. If you don't have this in your back pocket, then it's not clear what any of this had to do with Pythagoras at all. So what do we do? I mean, how do we connect those? Side note, if you want to get this Euclid solution, you can get the same way we just did this factoring problem. Just start with the unit circle instead of the circle with radius root 2, and you can get these formulas. Okay, so let's go back and think about that second proof a bit more. The main step was finding that one-to-one birational correspondence where rational numbers corresponded to rational points on the circle. Okay. If you think about how we did that, the circle really wasn't involved. I mean, we could have had any quadratic equation here. So if we took any conic section with rational coefficients and we have one rational point, then we could go through that exact same process and get a one-to-one birational correspondence where points on the conic correspond to rational numbers. So a point corresponds to the slope from it to our specific point, and then a slope corresponds to, well, start at our specific point, see where else it crosses. It's going to be some ugly formulas. We don't know what they are, but the point is, since all these coefficients are rational and x0 and y0 are rational, whatever we get here, it's going to be some rational function. So sure enough, we'll get a one-to-one correspondence between rational numbers and rational points on the conic. And at this point, we can kind of go all mathematician and just say, well, any conic is birational equivalent to Q, and so that means any two conics must be birational equivalent to each other. And well, since the points of the unit circle are parameterized by Pythagorean triples, then that means that the rational points of any conic must be parameterized by rational functions of Pythagorean triples somehow. And that would work, that's fine. But kind of going all highbrow like that, I mean, really the geometric picture is very simple. And so in just a second, I'm going to switch to my tablet where I can draw a picture. And so I can just show you the geometry behind it. Right quick, before I do that, let me just state the final result. It takes a little more work to show that we have actual linear something instead of rational something. But if you have any of these projective conic things, you're looking for non-trivial integer solutions, well, as long as there's at least one of them, then all of them are given by some matrix applied to Pythagorean triple. And so, for example, we did the p squared plus q squared is 2m squared. We got p plus, or a plus b was p, a minus b was q, c was m. Just for another example, I pulled out a random parabola if you want to check it. The integer solutions to that parabola equation are given by that one. So, all right, let me switch to my tablet where I can draw a picture of the geometry. And then we'll also talk about related construction, which kind of goes into group theory and elliptic curves. And I'll give you a few exercises to think about on those. So now that we're switched to the tablet, just draw a picture of this birational correspondence between two conics. We saw that algebraically you could potentially have some pretty nasty formulas, but the geometric picture is really simple. We've got two conic sections and a designated base point on each one. And so our correspondence is, well, if you give me any point on the first conic, I just connect it to the base point, and then I draw the parallel line from the base point on the other conic, and then wherever it intersects, these two correspond to each other. So the geometry behind this those horrible formulas is actually just really, really simple. It's just draw a line, draw the parallel line, where they cross, those correspond. And then if you're wondering what happens to the base point itself, well, you can imagine as my chosen points gets closer and closer to the base point, then the secant line gets closer and closer to a tangent line. So I'd have that guy there. So if I draw the parallel line over here, the base point would get mapped to wherever that crosses. So, okay. And then going back to the very original topic of the video, if you have a homogeneous quadratic in 3 variables, basically we said Pythagorean triples solve all of them. And how exactly does that work? Well, you need to start with one particular solution. So we've got some x, y, z that works. We can divide through everything by z squared to get a conic, and divide this by z squared to get a base point. So we've got base point x0 over z0, y0 over z0. And then, of course, we also have the unit circle. So unit circle with its base point of 1, 0. And so if you give me any Pythagorean triple, ABC, well, the first thing I'm going to do is find the greatest common divisor. And just note that down. Let's call it K. And then ABC also gives me a point on my conic. So I've got A over C, B over C, or point on the unit circle, that is. So I connect that to 1, 0. I draw the parallel line on my other conic. Wherever it intersects, I can write that as over a common denominator. So say it's x over z, y over z. And then I remember my greatest common divisor. So the triple I associate to ABC is then kx, ky, kz. And that gives us a 1-to-1 correspondence between Pythagorean triples and integer solutions to our general homogeneous equation. And like we said at the very end of that last video, it takes a little bit more effort, but you can show that this correspondence is actually just given by XYZ is some 3 by 3 matrix times ABC, or almost anyway. It might happen that you have to take out a common factor. Like you could start with a primitive Pythagorean triple, but there might still be a common factor in XYZ you have to take out. But otherwise, this correspondence really is just matrix multiplication. Cool. All right. Well, that's it for the main part of the video. But for more advanced viewers, I'd be a little remiss if I didn't connect this to another construction, which is the group law on a conic section. So namely, if you have any conic section and you have a distinguished base point, which we're now going to call 0 because it's going to be the identity of an abelian group, then it turns this conic into an abelian group by, well, if I have 2 other points, so here's A, here's B, I draw the line through them, I draw the parallel line through the identity, and wherever it crosses is A plus B. Okay. And similarly, if I want to do inverses, so if I've got A, well, I imagine the tangent line at the identity, I draw a parallel line, wherever that crosses is minus A. All right. So here's a few exercises. Most of them aren't terribly hard, but for one, show that this is the usual group law on the unit circle. So I'm going to give you hints for all these exercises. So for this one, all you need to do is show that, okay, I've got 1. If I've got a couple angles here, so say here's phi and here's like psi. So about right here should be phi plus psi. Then what you need to show is that that line and that line are parallel to each other. That'll show you this is the usual group law you're used to on the unit circle. Okay. Second up, as you can imagine, associativity is not completely trivial. And so rather than actually proving it, I just want you to think about, what does associativity mean as a geometric statement? And then once you figure out what that geometric statement is, then notice that that is actually a special case of Pascal's mystic hexagram. So actually, if you're familiar with elliptic curves, that's how you go about proving the associativity for their group law, as well as you reduce to an even specialer case of Pascal's mystic hexagram. Okay. And then 3. This one's pretty simple. So we spent most of the video talking about we've got 2 conics with base points, and we have this correspondence between them. So you might ask, well, is that correspondence a group isomorphism? Well, the first thing you would need is for it to definitely take the identity to the identity. If we just choose our base points at random, there's no reason to think that that's going to happen. So just what's the condition for taking the identity to the identity? So I guess your hint is this is like a one-sentence answer. I mean, it's pretty straightforward when you think about what it means. Okay, and now let's get into kind of the meatier one. So this group law that we wrote down very much resembles the group law on elliptic curve. So just let me remind you of that if you haven't seen it, whatever. So we got our identity. So let's pretend this was an elliptic curve. We have A and B. So on an elliptic curve, you draw the line through AB, and then you look for the third point where it intersects the curve. Of course, on a conic, it's not going to intersect at a third point. So we can kind of imagine that it intersects somewhere out here at a point at infinity. Then you're supposed to connect that third intersection point back to the identity, and wherever it crosses the curve again, that's A plus B. So, well, if I connect the point at infinity back to the identity, that just means draw a parallel line through the identity. Right. So it actually is exactly the same construction, just with this idea that our extra intersections are out here at infinity. One very nice thing about elliptic curves, if you have a birational correspondence between them, then as long as it maps the identity of one to the identity of the other, then it's automatically a group isomorphism as well. So the group structure for elliptic curves is very strongly tied into their rational structure. And so we probably ask, well, for our conics, is that true as well? So if we make our conic correspondence have the identity mapped to the identity, is that going to make it a group isomorphism? And the answer is no. In fact, probably the simplest thing you can write down is a counterexample. So let's just write down what happens for the unit circle and this 2x1 ellipse. So let me put a few more points in here. So here's A, here's B, here's A plus B. So my corresponding things over there, well, B is easy. I mean, I draw a parallel line. So B prime is still just there on the west pole there. A, well, you might hope it goes to the north pole, but if I draw this line, I need a line of slope 1. A line of slope 1 is going to intersect somewhere over here. So it doesn't wind up at the north pole this time. And similarly, A plus B is going to wind up down here. On the other hand, if I add A prime and B prime in this ellipse, well, I connect them, and then I draw a parallel line through my base point, and so A prime plus B prime is down there. In particular, it's not the same as A plus B prime. So this is not a group homomorphism. Well, shucks. Well, let's try to figure out what went wrong. So first thing, so just looking at this specific example, if you go through our birational correspondence, you can check. So part 1, check that this is the parameterization you get for this ellipse. Okay. Once you've done that, notice there is a whole lot more natural parameterization for that ellipse, which is just change the x and leave y and z alone, right? So if I go 2a, b, and c, that is a perfectly good parameterization for that ellipse. And that one does make it isomorphic to the circle. And so the second part, or next exercise, I guess, is first of all, show that's an isomorphism, but then more importantly, figure out what does this parameterization geometrically do that the first one doesn't. So the second one leaves something invariant, and that's the key to making this correspondence an isomorphism. So figure out what that thing is. Okay. All right. Well, next up, notice the second parameterization isn't really that different from the first one. So all it is we're going to still just map points over, but before we make the corresponding line on the ellipse, we're going to cut the slope in half. So Pythagorean triple, we write down the slope from it to the base point, then we divide that slope in half, and then we draw the line with half slope, and wherever that intersects, that's going to be our new point. So if you so check that if you kind of put all that together, you get this 2a, b, and c parameterization of the ellipse. And so that leads us to our final question, which is, well, is that enough? I mean, is it always possible that by inserting an appropriate slope adjustment like that, you can make our birational correspondence into a group isomorphism? So, is that enough? Is there more obstructions? Let me know what you think in the comments. And yeah, thanks for watching, and hope you have a great summer of math.